Bader, emeritus from McMaster University. He told me not to say much because he has many things to say. So I can only tell you that he has a Bachelor's of Science degree and a Master's of Science degree from McMaster University in Hamilton, Ontario. It is Hamilton, which is across the lake somewhere north of here. And he says they don't get as much snow as they do in Buffalo, and probably not as much as we do here either from the lake. He has a PhD in experimental chemistry from MIT, and then he did some postdoctoral work at Cambridge, England, and he will tell us how he got interested in theory and switched from experiment to theory. But he went back to McMaster University, where he joined the faculty in 1963 and remained there until becoming emeritus. Actually, he and I overlapped for a few weeks, I guess, in Parr's group at North Carolina when I was a grad student, and Richard Bader came in and we shared an office. And I remember he would come in the morning and sit down at his desk. It was mostly paper and pencil work back then, and he would be writing away with formulas and things, and he would comment that, you know, thinking makes me warm. He felt the heat in his brain from all this heavy thinking, which he was doing. He'll smoke during the lecture, you'll see it. And then I noted in the PChem book we're using now we use for 301, there was some part in that book that talked about the number of watts the brain produces. And I suppose you were producing double that because you felt it. Now, Richard has a number of publications down here, so if students or faculty are interested, they could come down and mull through them at the end and take something home to read. But I don't believe the freshmen will be given tests on those, will they? They might be, but they're not enough to go around. And Richard is very happy with this honorary book that was published last year, Quantum Theory of Atoms and Molecules. It's a collection of contributions from quite a number of authors, and he wouldn't mind if I would read this. The Quantum Theory of Atoms and Molecules, developed by Richard Bader. This is a review of the book, and co-workers. I think it is. You didn't write this, did you? This is somebody else's review of the book.
Sorry, what?
This review of the book is something that was published, or it's on the back of the book or something. I'm teasing, don't worry. And co-workers is now having enormous impact across many areas of chemistry, physics, and biology. And this volume of collected works is dedicated to him on the occasion of his 75th birthday.
I'm 76.
He's 76. It is a timely publication since Bader's influential 1990 monograph, Atoms and Molecules, A Quantum Theory, published nearly 2 decades ago, has received over 3,000 citations, more than half of them in the last 5 years, 2002 to 2006. So Richard Bader is here for our Frontiers lecture now, and it's a pleasure to have him. And I must mention he's the ever-ready lecturer, and before he begins, there's the plaque. So I'll let Professor Protasevich give it.
Well, normally our department chair, Larry Sayre, has the honor of delivering this gift to the speaker, but he's unable to be here today. So today it's my pleasure, on behalf of the department, to give you this plaque.
If you don't want to wait until after my talk, maybe I won't earn it.
Well, we have the right to take it back if we don't like it. But honestly, this is the 67th year that we've been running the Frontiers in Chemistry lecture series. So we're giving you this nice plaque with the date and name Richard Bader on it. So welcome, and we appreciate the fact you've traveled so far to come here.
For my study wall.
Yes.
Okay, now it's my turn to thank you. It's a privilege.
Professor Bader, your
I
microphone.
consider it a privilege.
Oh, could you turn on your microphone?
Oh, yeah. Is it on? Okay. I consider it a privilege to have this opportunity of telling you about how I spent my life thinking about chemistry and science, particularly to the young people whose minds are still uncluttered and open to new ideas, new concepts. That's what I want to talk about today. We're going to go from Dalton to Schrödinger to chemistry, to atoms and molecules. It's a very exciting journey, all right? Nothing happened. Why does it do that? Why? How do I get rid of that? Ah, there, okay. All right. Two of my heroes. I don't have too many, but these are two of them. Dalton, 1805, when he first presented his ideas. Schrödinger, when he wasn't messing around, developed wave mechanics, all right, quantum mechanics. Schrodinger's wave equation. Now, what I'm going to do in this talk is show you how you combine these two ideas, which are two of the greatest ideas in their respective centuries, combine them to get the theory of an atom and a molecule. Get back all of chemistry, okay? All right, now as a matter of fact, one of the reprints down here, this one, is my most recent reprint, and it shows you how you can, the original theory requires a lot of fundamental physics, and that's what makes it important. You can derive the theory from fundamental physics. You can also derive it heuristically. Anyone with just a knowledge of Schrödinger's equation can go home tonight and recover the whole theory. This is not my theory. What I'm going to present to you is a theory of quantum mechanics. And everyone and anyone with a knowledge of Schrödinger's equation and the observational basis of the electron density can derive the theory entirely on their own without any help from me. No coaching. You can do the whole thing on your own. That's called science, right? That's what I think science is. Now, I started out as an experimentalist with Professor Swain at MIT, and I was fed up with I wasn't happy. I'll try to tone my language down a bit. I was unhappy with the existing orbital models. Chemistry had seemed to have gone in a funny direction from measurable things. As an experimentalist, I found that when I went to orbital models, I said, but these things there's nothing here I can relate to measurement directly. None. The orbital theory, when properly applied to spectroscopy, et cetera, et cetera, et cetera. I'm talking about the orbital models that people use to explain this and explain that. And so instead, as an experimentalist, you turn to something that's real, the electron density. And you find in the topology of the density a definition of an atom, the bonding between atoms, and most importantly, the boundary condition that enables you to extend quantum mechanics to an open system, an atom and a molecule. If you got a molecule, you want to talk just about a piece of it, that's an open system, right? Exchange energy, momentum with all of its neighboring atoms. As the atoms vibrate around, obviously they're going to change. So it's an open system in the usual thermodynamic sense. And that's what we're going to do, is develop the physics of an open system. I'm uncomfortable with my jacket. Can I? Sorry, using up precious time here. We've got to do all of chemistry, so we've got a lot of ground to cover. Okay? Shocks. Now, the resulting theory we call the quantum theory of atoms and molecules. Now this, unlike whatever Professor Hoffman told you last week, recovers all of the concepts of experimental chemistry, of atoms with characteristic additive properties. You think about what chemistry is to you. I want you to think about functional groups. Atoms, functional groupings of atoms with characteristic and additive properties. Structure, molecular structure, and structural stability. Not just structure, but how you change one structure to another. Which structures are stable, which unstable. The localization, delocalization of electrons. That's determined by the electron pair density. It's this that underlies all the ideas of the Lewis electron pair model, Vesper theory, resonance. You can take all those ideas and you can give them a quantum mechanical basis. That's where we're going. Now, Rael and I correspond a bit. This is just from correspondence last December 13th. And we have a fundamental difference, as he says here. I also have philosophical revelations about the reductionist framework in which aim resides. I believe the most interesting ideas of chemistry are not reducible to physics. He's published these comments. I'm sure he said comments along these lines in his talk. I think we have a fundamental difference of opinions on this matter. Now, I agree. First of all, I want to make it clear that everything I say today, I will not offer a single opinion. Everything is based either on physics or observation, okay? I'm going to present you with a theory, which is just quantum mechanics, extended down to an atom at a time, that recovers all measurable properties. Quantum mechanics predicts everything that you can measure. So this theory predicts everything that you can measure, all right? The theory of atoms and molecules. Now, when Weyl talks about reductionist framework, I think the application of the scientific method, experiment, observation, followed by appeal to theory, which hopefully leads you back to new experiments and new observations, that's called the scientific method. The only thing reductionist about the application of the scientific method is to reduce the fuzzy thinking that it replaces. As you push back the boundaries of what we know and the boundaries of our knowledge, you replace uncertainty. You're reducing the uncertainty with the beauty and precision of physics, all right? So that's the only way I can see any reductionism as a reduction in our fuzzy thinking, okay? I firmly believe that. I think that anybody who says that chemistry and the important concepts of chemistry somehow lie beyond the boundary of physical understanding, to me that smacks of mysticism, but we all can have our own views on that. All right, now I'm going to tell you about the events that led me to try and find the basis of an atom and a molecule, aside from my basic love of chemistry. We go all the way back, and this is just a summary of what we ended up doing. We ended up extending quantum mechanics to an open system. And I'm very proud of this because I started life as a physical organic chemist, and you see action, action, action. I didn't know what the action or the action integral was. I had no idea. But I learned it. And I learned it because every step I'm going to outline here always said, what does physics say about this observation? Now, this is what science is all about, isn't it? Observation and applying physics to observation. Forget your preconceived, prejudiced ideas. And there are so many of those around. The only thing that held me up at times was I would say, gee, how can that be? That doesn't go along with what I believe. And of course, what you believe is wrong, and you have to switch over to what you find. You think about that, all right? So many people find it extremely difficult to accept new ideas. Look at, from 1805, Dalton and the development of molecular structure hypothesis. A molecule is a collection of atoms linked by a network of bonds to give a structure. This evolved very quickly after Dalton. Before 1900, we had the whole idea of the molecular structure hypothesis. This comes from experimental chemistry. It's got to be true. Central to this is the idea of a functional group with a set of characteristic transferable properties, allowing us to identify the group or predict the properties of some molecule which this group occurs. What happened? You just unhooked yourself. Oh, I'm sorry. All right. I wave my hands too much. We're taking up time. Quickly, quickly.
I'll move quickly. My students are tough.
I'm already talking too much. That's my heavy breathing, okay?
There you go.
Don't ever smoke. If there's anybody here who smokes, quit. Go home tonight and never have another cigarette. Look at me. You want to see what happens to you. All right. Dalton's atomic hypothesis has emerged as the operational theory of chemistry. Now, I went to theory. I was doing my PhD with Professor Swain at MIT, and we would argue about making and breaking bonds between atoms, and it was clear that he had his pictures of atoms and bonds. I had my picture of atoms and bonds. I don't remember what it was, but neither of us had the same ideas. We used the same vocabulary, we had different dictionaries. And of course, neither of us knew what we were talking about. Here is the basic fundamental language of chemistry, and it was not related to physics. And molecular orbital theories, Hoffman himself says there's nothing in molecular orbital theory that recovers the concept of a functional group because orbitals are spread over the whole molecule, and there's nothing to suggest that there's something special about just a piece of a molecule. So molecular orbital theory grew. The concept of a functional group in chemistry was downplayed in theory, and you couldn't find it. But I knew as an experimentalist, it had to be there. It's so deeply rooted in your thinking. When you walk into a lab, it's how you think about a problem. So theoreticians told me, oh, you're wasting your time, Richard. Anyways, 1911, Rutherford came along, nuclear model of the atom. The nuclear electron force is the dominant force in any atomic, molecular, solid state system. And it's the only force, attractive force in chemistry. It is the force responsible for chemical bonding, and it imposes on the topology of the electron density the dominant feature that leads to the idea of atoms and molecules. It should follow from that. It's by far the major force acting in a molecular system. When I say molecule, I mean crystals, liquids, anything you like. Okay, 1926, Schrodinger's wave equation. We had them on the picture before. Now, Schrödinger turned out, knew a lot of physics, and he derived Schrödinger's equation by writing out some strange beast he called a wave function. And when he varied this, the expressing the energy in terms of this new thing called a wave function, minimize it to get a corresponding equation, which we call Schrödinger's equation, he used what is in effect was a constrained form of the action principle. Now the action is fundamental, not just to quantum mechanics, but to physics. I wish I'd have time to talk about. It goes all the way back to the 1700s. The idea that in any physical change, there's a quantity called the action, and that action is minimized for that change. What a simple, powerful idea, right? It's breathtaking. And if you're an inorganic or an organic chemist like I was, and you suddenly learn about all this, you say, this is amazing. This is really exciting. How can I use these ideas to understand chemistry? Dirac's, then you go off and you got to start reading physics, so you read Dirac's book. You don't have to read the whole book, but read a part. Transformation theory. If you haven't had quantum mechanics yet, but those of you who've had it, you know the importance of transformation theory. And Dirac asked a really important question. He said, look at it. This action approach, the Lagrangian approach is called, to physics, is more fundamental than the usual Hamiltonian approach, which sprung up, of course, after Schrödinger's equation, which says H psi equals E psi. It gives you back everything. You don't have to assume H psi equals E psi. It gives you back Newton's equations. Everybody's equations are derivable from one single principle. So he said, why can't we have this principle in quantum mechanics the way we have it in classical mechanics? And he wrote down a limiting expression based on what would be if you take a quantum mechanical expression that tells you how you change from time t1 to time t2, what would the limiting classical expression be? I won't give you the details. But then 1949, Feynman took that idea and he said, look, I'm not at the classical limit. I want the whole quantum mechanical limit. So instead of taking just one path between T1 and T2, the way Dirac did to get this limiting expression, Feynman said, I'm going to consider all paths. I can't ignore any of the paths because you can't define a single trajectory in quantum mechanics. And he developed Feynman's path integral technique. This gives you Schrödinger's equation, the commutation relationships, everything from a single principle. Now, a little bit later, 2 years, Schrödinger came along. And he said, I'm going to use Dirac's statement that you can get a differential characterization of this transformation function from T1 to T2. And he ended up postulating what he called the principle of stationary action, which is a differential form of Feynman's path integral technique. Now, these are really great ideas. Now, look at it. Don't go through life never having read. Read Feynman's papers. He's so readable, so understandable, easy to follow. Get hold of his 1949 paper in phys red. Give it a try, not before you've had any quantum mechanics, but after you've had some. The ideas there are really the fundamental ideas of physics. Now, what we were able to do is we went back, we said, what is an atom and a molecule? We went back to Schrödinger, 1926 paper, and we said, Schrödinger said he's going to apply his variation over all space. What would you get if you applied it to a piece of space? The question we ask. That's the obvious question. Do you want to look for an atom and a molecule? I don't know why no one had ever thought of asking this question before. Why wouldn't they ask it? It's the obvious question you ask. If you pick a piece of space, you have to have a boundary condition, right? Always a boundary condition that picks out the important physics and discards the rest. And guess what the boundary condition is? It's stated in terms of a property of the electron density, which is a direct result of this topological feature of the electron nuclear force being the major force, as I'll describe. Really exciting. Right, in 1975, we showed that you could derive the Virial Theorem, and hence all other theorems, for an atom and a molecule, starting with Schrödinger's first paper. Only you simply applied it to a piece of a system instead of the total system. Then we spoke to our physicist friends, and they said, oh, Richard, what you're doing is all well known. You're just doing Schwinger's principle of stationary action. So we read all of Schwinger's papers, and indeed, we could take Schwinger's work, where he varied the time limits on the system. We showed you could also vary the spatial limits if you took a piece of space, and we could cover all of physics. So just as Schwinger recovers all of physics for the total system, we showed you could recover all of physics for a piece of a system. And I was a physical organic chemist, right? You know, I once met a theoretician at a meeting after I'd criticized something he had said in the 60s. And he said, Richard, you are just a physical organic chemist. I'm a theoretician. You must never criticize my work again. Can you imagine, right? I laughed then and I laugh now, right? It's ridiculous. He's still working on the bonding in H2+. He spent his whole life thinking about bonding in H2+, and he's still working on it. All right. Now, oh, gee. Okay. Well, regardless of how far I get, let's make it interesting. That derivation I just told you about, that was really exciting. And we showed how you could get the whole theory of an atom and a molecule from fundamental physics using the variational principle of physics, right? Variational principle in conjunction with the idea of the least action. But then, that's great, but then at the same time, most physicists don't know about Schwinger's principle. I don't think any chemist knew about Schwinger's principle. So nobody really believed in our proof that we really did have a theory of an atom and a molecule. And people don't like learning new things. I enjoy it. It's what makes life as a scientist interesting, right? You get a chance every day to learn something new. So anyways, that's why I finally wrote this paper. What you can do, anybody who knows Schrödinger's equation, H psi equals E psi, can go home tonight and he can derive everything I'm going to talk about in this talk, okay? Heuristically, not as fundamentally, but just as powerfully. Now here I've got H psi equals E psi and the complex conjugate. That's quantum mechanics. You have not only the wave function, you have its complex conjugate. And observable properties are driven by psi star. And here I've written it in the Dirac notation of a Brown-Ket. Because now what we have to do, and I'm going to keep this to a minimum, just a little bit of physics. In addition to Schrödinger's equation, the other fundamental piece of physics is the Heisenberg equation of motion. Once you have a wave function, what do you do with it? Well, you want to calculate the expectation values. That's what you do with it. And you can do more than that. You can get how does the expectation value, its observable value, change with time? That's called the Heisenberg equation of motion, which actually preceded Schrodinger's derivation of quantum mechanics. So these are the two fundamental pieces of physics. You use Schrodinger's equation to get the wave function, the state vector wave function. They're not waves. And then you use this to predict the properties of matter. And from the Heisenberg equation of motion, you get all the theorems of quantum mechanics. All right. So here's the average value of some property determined by the operator A, and here's its time derivative, and it's given in quantum mechanics by the average of the commutator of the Hamiltonian and the operator A. Now, if you have a system in a stationary state, this, of course, equals 0, because there is no time dependence. But it's interesting, you can derive this independently. Expand the commutator HA minus AH. Now, the beautiful quantum mechanics, right? H can act to the left and give E psi, A psi, or it can act to the right to give E psi, and again you get minus psi, A psi, and you get 0. Now this follows from the Hermitian nature of H. And what's really interesting, and we found to our complete and utter surprise, is when you go to a piece of a system, in general, operators are no longer Hermitian. And you can't go from here to here and say you get the same thing. And because of that, you get something entirely new. If you have a piece of a system, and here is neighboring another piece, when they jiggle around, things are going to get transferred between them. How does quantum mechanics describe a transfer? In terms of a current. Schrödinger introduced the current along with the electron density in his fourth paper in 1926. So you're going to get a current flowing between the atoms. For every property, there's a corresponding current density. In a stationary state, you freeze this, and it tells you in a given instant, this is the influence of the surroundings on a given atom. So at first we said, my God, we're getting a variation principle and it's not vanishing. Little did we know we had rediscovered Schrodinger's principle, but you learn that. So for an open system, the average of the commutator doesn't vanish. It's given by a surface integral. This is just an integral over the surface of the current for the property A. Where here's the current. Now, almost done. Now, we can go all the way. Last equation. I see somebody walking out, the last one, right? If you're doing just a piece of a system, not only are operators no longer Hermitian, they're not necessarily real. Their expectation values are not necessarily real. So you always have to take a quantity plus its complex conjugate. A quantity plus its complex conjugate is always real, right? And so here's that final equation. You've got to realize now that with this equation, and it's time, you can write the same thing for a time-dependent system. You've got all of the theorems of quantum mechanics, and they're all applicable to a region omega if we can find the boundary condition that makes the predictions of this equation agree with the experiment, right? We've got all of physics sitting here within our grasp, but we've got to find, does it apply to any old subsystem atom omega or to only special ones? Okay. What do I say there? Yeah, okay, I don't give the answer. We're going to find the answer. That the boundary condition is an inescapable consequence of the dominant topological property of the density, exhibiting a maximum to nucleus. So let's go find the boundary condition we need to make this equation of motion applicable. All right, now, here's the electron density in the plane of the nuclei. I could take any system, a complicated one, a system one, a crystal, whatever. Let's take a very simple one, BF3. Here's a display of the density in the plane of the nuclei, where the density is displayed in the third dimension, okay? Now all these things go to a very high peak, which we cut off. Now, in addition to those peaks, which are pseudo-critical points, points where the derivatives of the density vanish, there is certain of the nuclei, each boron is linked, a boron is linked to each of the fluorines by a saddle point. Here again is a point where the first derivative of the density vanishes in this direction, that direction, and in this perpendicular direction, okay? Now, those are the two principal characteristics. Whenever any two atoms come together, they both have a density peak, and they'll always have such a critical point between them. All right. Now, here's the same density now displayed in the terms of contour values in the plane, the same plane. And over here, I've displayed what's called the gradient vector field. You know, it's amazing. It's very exciting to do something new. It's even more exciting when you find that just before you've started working on a problem, the mathematicians have already solved it. Mathematicians had considered the abstract problem of what is structure and what is structural stability, and they considered in particular simple gradient, simple fields such as the density. And they said what you should look at is the gradient vector field of this property. And in its gradient vector field, you'll find all the definitions of structure and structure stability. This was all sitting there, waiting for us to apply. So here, we're going to go to points in space, and we're going to say, let's calculate the gradient vector of the electron density at each point in space and follow it and see where it goes. Now, you know the gradient vector of a scalar field. Scalar was the word I was looking for. A scalar field always points in the direction of maximum increase in the scalar. So, of course, all these trajectories, all of them, will terminate at a nucleus, right? That's where the density is a maximum. In 3 dimensions, you're going to have a whole set of trajectories, all of which come in and terminate at, I should be using the pointer. Have I got a, this. Well, forget this. Thank you. Okay. All these trajectories terminate in a nucleus, and that'll happen in each atomic region for each nucleus. They obviously map out a region of space called the basin. This region of space associated with all the trajectories that terminate at a given nucleus is called the basin. When you apply this to any kind of atomic system, it breaks it up into atoms. It's so simple. Here's a fluorine atom, here's the boron atom, and they're all separated by surfaces. And there are no gradient vectors that go across that surface. You say, well, what about here? Well, this is one of those critical points where the gradient vector vanishes. There are 2 trajectories here, but they originate here. One goes here and one goes there. So these are surfaces. Each atomic region is bounded by a surface which is not crossed by any trajectories of grad rho. In other words, grad rho dotted into a vector normal to the surface at any point is 0. We call them zero flux surfaces. All right? Now, how about these critical points? How about the trajectories that terminate and originate at these critical points? Well, here they come. And you can see what's happening. There'll be a whole set of trajectories. There'll be a whole set of trajectories which come in. And in the end, they don't terminate at this nucleus or that one. Instead, they terminate at this critical point in the density. And in 3 dimensions, there'll be a whole set of these which come in and terminate there and define a surface, an interatomic surface. So you've got 2 definitions of an atom. An atom is a basin, and its attractor. I can never find this stupid thing. A basin and its attractor, or it's a region bounded by a surface of 0 flux in the gradient vector field of the density. Clearly, the trajectories that terminate at the critical point will define a surface which is not crossed by any gradient vectors of the density. Then we get an added bonus. Oh, what happened? Oh, they're already here. How about the trajectories that For each critical point, there's a single unique pair of trajectories, one of which originates at this critical point and goes to one nucleus, originates at the same critical point and goes to the other nucleus. They define a line through space along which the electron density is a maximum. Now, wherever, for the rest of your life, when you translate a classical structure using the ordinary rules of chemistry, you realize that every time you draw a line, what you're really mapping out is a line along which the electron density is a maximum with respect to any neighboring line. These lines recover all the structures of chemistry and allow you to define a structure in those cases where people argue about is there a bond, isn't there a bond, et cetera, et cetera. All right. So now we've got atoms, we've got bonds, and these are indeed, when you use these surfaces back in that equation of motion, you recover all of the properties predicted by quantum mechanics. And there are many, many, many atomic properties that are experimentally measurable. Don't let people tell you there aren't. They're all around. What started in 1910, started in the 1800s. Electric polarizability, heats of formation, magnetic susceptibilities. There are all kinds of examples. Now there are millions and millions of examples of where properties are transferable from one molecule to another. When that happens, you can measure them experimentally. And this boundary condition, in conjunction with that equation of motion, enables you to calculate any and all of these properties. All right, so go to a crystal. Here's a crystal of potassium, magnesium, fluoride of some kind. And here are the potassium, fluorine, and magnesium ions encased in their surfaces of zero flux. A beautiful idea for analyzing a crystal and crystal structure. Here are some molecular graphs. See if I get this thing going. Here are the chromium, iron, and nickel atoms in their carbonyl compounds. Carbon, oxygen, and the small red dots are these bond critical points. The points that define the origins of these lines of maximum density. So you see, we cover all the structures you would anticipate as a chemist. Now, I don't care how complicated the system is, this is always true. You can not only have open structures, you can have rings, and you can have cages. You have a ring, you get a yellow, here's a three-membered ring, you get a ring critical point. If you've got a cage, which is a region of space encased by rings, you get a cage critical point. So in the topology of the density of maxima, nuclear maxima, bond critical points, ring critical points, and cage critical points, you recover all possible structures that you observe in chemistry, right? Nice. All right, next. Now these ideas are new and they're useful. Gibbs, just down the line here in West Virginia, here's a compound of nickel and sulfur, and this is a good conductor. Now, in the top slide, it shows all the molecular graph, all the bond paths linking the sulfur end. Why can't I see this thing? What am I doing wrong?
Use the lower button. Yeah.
Oh, red. All right, good. All the bond paths linking the sulfur and the nickel atoms. Here are the bond paths just linking the nickel atoms. And it's not that different from the bond path structure you get in nickel metal. And this is a really good conductor because these are like molecular wires. All the nickel atoms in this crystal are connected to one another. It's a really good conductor. Now, if you go to NIS, another compound of nickel and sulfur, here, now you get triads of nickel atoms, but they're not connected. This is a very weak conductor, and it conducts only through a hopping mechanism. So I want you to realize that. Now look at it. You have a whole new way of looking at things and predicting the properties of materials and understanding the properties of materials. If you try and analyze this using ordinary methods, you get a lot of trouble. This makes it extremely clear, right? Now we're only beginning. Here's a dynamic molecular graph. What about changes in structure? Clearly, as nuclei move and vibrate, the electron density is going to change. You could change its topology. You could create or destroy critical points. And every time you do that, you're going to change the resulting structure. Now, there are many, many systems, labile systems, we call them in chemistry, where the electron density is rather flat. When the electron density is already very flat, you can move the nuclei with very little change in energy. And when it's flat, suddenly it goes absolutely flat. That means two critical points have merged. They annihilate one another. You break the bond and you get a whole new structure. Now here, a beautiful recent example. Here's an iron atom, 3 carbonyls. Here's a carbon atom, and three methane, whatever. Methane, thank you. Where's the button? Methane carbon atoms. Now, as this molecule vibrates, look what happens. You form bonds between the iron and these bonds. There are no bonds. Bond paths. Bond paths between the iron atom and these methane carbons. And every time you do, you form a ring, so you get a ring critical point. And these are continuously forming and breaking every time the molecule undergoes this particular vibration. Now, this occurs all throughout chemistry, or it can be a very high energy change. And you can follow the course of any chemical reaction and see where the bond paths are made, where they're broken, how one structure changes into another. There are only 2 possible mechanisms for changing structure, called the bifurcation mechanism, another one called the conflict mechanism, and that's it. You can get a structure diagram for any system that defines all possible structures and all possible changes in structure for any system. When people tell me that the theory of atoms and molecules is not predictive, I feel like pounding them on the head, because it exhibits a complete ignorance of what this theory can do. It predicts everything and enables you to make new predictions and talk about things you couldn't even think about before. It's a beautiful theory. Look at that, right? You go home and you read the mathematics behind this. You can go as deep as you want into the mathematics and take just a summary view, or you can go into deep, and it's beautiful mathematics. So everything I'm saying here is grounded in physics, mathematics, and observation. Experimentally, this is a labile system. Now you understand why. Here's another good example. Here are 2 alloys. One copper gold, and the other one titanium aluminum. They have the same crystal structure. That means if you go in and scatter X-rays off these atoms, they have the same basic structure in terms of the atoms and their placement relative to one another. But their charge distributions are different. Just because they have the same crystal structure doesn't mean they have the same charge distribution. Now this top one, this is just like copper metal. It has the same FCC structure. Each copper is bonded to 12 nearest neighbor gold atoms, and you have this structure which is ductile. You can move these atoms around, and you don't make or break any of these bond paths. The structure is invariant. But if you come to this one, now in addition to these 4 bonds, each aluminum is bonded to a neighboring aluminum. And now we have a bond critical point in proximity to a ring critical point, and now when the system vibrates or you twist it, these 2 approach one another. The electron density here is very similar. They approach one another, they annihilate, and you've broken the bond. And you say, gee, I've just had a transgranular failure in this. And that's why. You see the power of this. You can now design high temperature alloys for use in jet engines and understand now why some are better than others. And people are doing these things now with this approach to metallurgy. Okay, so what's next? Oh, Jesus. So you see, it took too much of my time, right? But look, I'm going to do this. It means I might have to leave off something at the end. But what I want to emphasize to you today, as undergraduates and people embarking on a career in science, Stick to observation, and then apply theory to your observation, okay? Forget all the silly models, forget all your preconceived ideas. We were really lucky in the 60s to collaborate with the Mullick and Rotan group at the University of Chicago, and they gave us these beautiful, beautiful near Hartree-Fock wave functions. You couldn't measure densities accurately in the 1960s, but from these wave functions, we could calculate excellent reputations of electron density. These were our experiments. And lo and behold, just diatomics, but we could see chemistry. Look at here. LiH, LiO, LiF, hydride, oxide, fluoride, totally different partners, and yet look at how similar the lithium ion is in all these cases. You can get the charge by, here's a zero flux surface, add up all the density there, and you get, subtract the nuclear charge. Here's plus 0.9, 4, 9, 3, 9, 1, decreasing, of course, as you would expect. How in heaven's name can a lithium ion be so similar, whether it's bonded to a hydrogen, a hydride ion, or a fluoride ion? And you look at that and you say, my God, these are the groups, the atoms, the functional groups that chemists are talking about, right? Totally different environments, and yet they look almost the same. If they look almost the same, surely they must have the same properties. This is in 1972. So then you say, look at it. We were also studying at the time a kinetic energy density. It's something, a density that's easily expressible in three-dimensional space. And we made the remarkable observation, and this is still the most important observation I ever made in my life, that when rho was transferable, so was the kinetic energy density. You say, gee, because if there's a virial theorem for an atom and a molecule, the virial theorem is a theorem of quantum mechanics. No, we can get the statement for an atom and a molecule that relates the kinetic energy to the total energy of the system in the absence of external forces. First of all, the zero flux boundary condition has the important property that there's more than one way to define the kinetic energy density. They're all the same if you take a zero flux surface. Okay, get rid of that. A transferable kinetic energy for an atom would imply a definable atomic contribution to the total energy. If this is the kinetic energy for the lithium atom, minus that is the energy of that lithium atom. And you take all these energies, you can add them up. Adding up energies? Beta, are you seriously trying to tell me that you can partition the total energy of a molecule into spatial contributions? Electron-electron repulsions, nuclear-nuclear repulsions, electron-nuclear attractions. How can you possibly break that up? Because physics does it for you in terms of the fundamental fields that hold everything together. In this case, the virial field, the Ehrenfest force acting on the electrons. You see, in a single stroke, you'd have the atoms of chemistry. Characteristic additive properties, if the Virial Theorem applies. Now, of course, it does apply, because we're just seeing, we've recovered the equation of motion, which gives us all the theorems of quantum mechanics. So here's the equation of motion now for any observable general time-dependent case. You can use this now. You can put in any operator you want if you're interested in the force acting on the electrons. Remember, these are time rates of change. What's a force? A time rate of change. Force is time rate of change of momentum. Beautiful physics. You just put in P, and now you have the force acting on the electrons in any system. Now, all these properties are expressible in terms of densities in real space. The energy of a molecule, the potential energy, not just the kinetic energy, you can express as a distribution function in real three-dimensional space. That's how you can partition all of these properties into atomic contributions. If you're interested in defining the energy, you need the Virial Theorem. This term here gives you, is proportional to the PV product. You can use it to define the pressure acting on an atom in a crystal. You can use this one to understand the operation of the atomic force microscope. You can use this one, the atomic current theorem, to partition the magnetic susceptibility into atomic contributions. You can use these and any theorems you like now for any operator you like to answer every possible question you can think of in physics. There are all kinds of applications already made, many, many, many. That's important slide. Okay, so we go back now. Here we got the chromium, iron, and nickel atoms in those same carbonyl complexes. All I want to emphasize is, look at it. You can now go in and you can define any and all properties for these atoms. Here are their atomic surfaces. That's the chromium atom, and chromium hexacarbonyl. You want to know its charge, its energy. You want to know what happens as the things vibrate. You want to put it in a magnetic field, electric field. Do anything you want to do with it. And you can answer every question you can ask. All right. I've done all this. This statement that, here's a really important observation. Not only are all fields defined for any property, when the electron density is transferable, just as we saw for the kinetic energy, so is the kinetic energy density, so are all property densities. So now you understand transferability. I mean, it's common sense, isn't it? If I have two pieces of matter and they're identical, there's no way you would expect anything but them to give you the same properties when you took them into the lab to measure their properties, right? If they're identical, they've got to have the same properties. That's true whether they're macroscopic or microscopic, an atom at a time. If you have two atoms and they have identical charge distributions, and this happens in different systems, then those atoms make identical contributions to all of the properties of the molecules, including those properties that we described by mixing in excited states in electric and magnetic fields. Now, this has nothing, absolutely nothing to do with density functional theory. I don't understand, I can't predict this. It's an observation. When the electron density is the same over an atom and a molecule, and an atom in two molecules, all of its properties are as transferable as in the density. If it's not quite transferable, the properties aren't quite transferable. There's a direct parallelism. Now, just a quick example of this. Here's an example from a CH2 group. Well, believe me, it's true, okay? And you could do this for the density, the kinetic energy density, or the potential energy density. So here's a methylene group and two different molecules, and they're identical, just as Rossini found in 1910 when he showed the heats of formation are additive. Things really can be perfectly transferable between molecules. Right. No, they're not always perfectly transferable, don't misunderstand me. But that's the limit. And when you can explain that limit, then you understand the properties of atoms and molecules. All right, now I got to talk about bonding versus bonds, because I told you in my talk there are no bonds, right? The title of my talk. This is one point I agree with Professor Hoffman. He says there's no definition of a bond, and I couldn't agree more. It's an idea that's outlived its usefulness. Let's talk about what happens. Do I have, 5 minutes? Yeah, okay. What happens if you bring two atoms together? Now, Feynman answered this question back in 1939 with the Feynman electrostatic theorem. He showed that the force acting on a nucleus, a proton in a hydrogen molecule, is just the nuclear force of repulsion, and then the electrostatic force of attraction exerted on that nucleus by the electron density. That is, once you have the electron density, the whole understanding of forces acting on nuclei in a molecule or a crystal is just simple electrostatics. This incensed the theoreticians, particularly in Germany. You cannot explain bonding in terms of electrostatics. You won't find the Feynman theorem in any elementary or high school textbook. And that is a shame, because it's a theorem of quantum mechanics. And it's absolutely true. And people told Feynman, your theorem is too simple. Bonding is very complicated. Gee. And These people are like popes. Their statements are still. You should say, I'm tired of all this, I'm sick of it, and I want to change. I want textbooks that include the Feynman. Feynman's one of the geniuses of our generation, right, or previous generation or whatever. His ideas are incredibly profound. Look at what is a molecule? Any system. There's a relatively diffuse distribution of negative charge peaking at the nuclei, and the nuclei themselves are considered to be point charges. Now, if you want to hold two nuclei together, where do you put the density? Between them, right? And they say, well, that's too simple. It's not too simple. And when you do that, and you calculate now the force acting on, say, a proton or any nucleus in any molecule, you get the force curve, the static curve. And of course, you reach a point, the equilibrium depth, where the energy is a minimum, and that's where the forces vanish. But you see that? What is the bond energy, this energy here? It's simply the integral of this that you get by integrating this force over this distance. That area under the curve equals the length of that line. You can't have a bond energy if there wasn't an attractive Feynman force. No, I don't care if you got hydrogen bonding, covalent bonding, ionic bonding, van der Waals bonding, anybody's kind of bonding. They all result from this fundamental curve. The only way they differ is the depth of this well. It can be shallow or it can be deep. But they all are the result of a very simple mechanism. Negative charge attracting positive charge. And if you want a molecule that's stable and bound, you put the negative charge between the nuclei where it draws them together. Think if we could teach that in high schools. I don't know. It almost makes me cry when I read the Feynman theorem and the Virial theorem are the two most maligned theorems in quantum mechanics. They were the two most important theorems to Slater. But then we have this group of chemists that go around saying the Virial theorem is wrong because I spoke to God last night and he said, oh, no, it's all wrong. And then you have people say, oh, Feynman theorem ignores the kinetic energy. Oh, what a lot of nonsense. I don't know why we can't change these ideas. Look, here's two hydrogen atoms, 8 atomic units apart. And here's how the density changes as you bring them together. Density is removed from behind the nuclei, accumulated between them. What's the result? An attractive force. At this distance, you call it a van der Waals attraction. Now, the classical explanation of this is you have oscillating dipoles. If you had oscillating dipoles, which is an attempt to take 6-dimensional electron-electron correlation, express it in 3-dimensional space, which you can't do, you would actually get repulsion. So this is really, the van der Waals attraction isn't any different than any other kind of attraction. It's not oscillating dipoles. It's the accumulation of density between the nuclei as you push the atoms together. Do you know you can still have trouble trying to publish this? People say, but everyone knows. Everyone, I love, experts tell me that it's oscillating dipoles. And you point out in 1939, Feynman published a paper where he specifically contradicted that very statement. They say, well, Feynman, he's dead now, you know. I don't know. Now look at it. And I'll unfortunately finish here. I want to get across this. There are only two forces in chemistry. The Ehrenfest force acting on the electron density and the Feynman electrostatic force acting on the nuclei. Now the beauty of all this is the Virial theorem ties these forces together. The Virial theorem relates the virial of the Ehrenfest force on the electrons, that just means the force times acting through a distance, that's the virial, to the kinetic energy of the electrons. And part of this virial of the Ehrenfest force is the virial of the Feynman forces acting on the nuclei. So here you have a single theorem, the Virial theorem, which relates the kinetic energy, the potential energy, the total energy, and the Feynman forces acting on the nuclei, all in one beautiful theorem. And there's absolutely nothing about chemical bonding that you cannot explain using these theorems. don't know. Anyways, I haven't got time to do this in detail, but this is how these quantities, the potential energy, the kinetic energy, and the total energy vary for hydrogen, nitrogen, argon, and CO as a function of internuclear separation. And they all reach equilibrium here. Delta E is a minimum. And initially, delta V goes up, and delta T goes down, and then delta T goes up, and delta V comes down. It's demanded by the Virial Theorem. All I want to point out here is, look at covalent, polar, van der Waals, ionic. They're all the same, right? The only way those things differ is the depth of the wells. There's no difference between the bonding here or there. You know, there are still people out there who say the bonding in a van der Waals molecule, there is no chemical bond. It's held together by van der Waals forces. And you say, well, if you have two atoms held together by forces, isn't that a chemical bond? No. I don't know. I don't know what these people. The sad part is these papers are published and discussed back and forth and back and forth. The literature is full of junk like this. And of course, it's absolute junk, isn't it? Look at it. Here's physics. Oh, I'm sorry, but. Now look at, you're going to hear Hoffman say and others that a bond path can be present in a system where there are repulsive forces. And this irritates me because what's the definition of a bond path? A line of maximum density in a system where the forces are either zero or attractive. So how can it possibly exist in a system that has repulsive forces? And they never tell you what these repulsive forces are. They're always something mystical. They're not neither Ehrenfest nor Feynman. They're forces that remain undefined. Look at it. Once we cross into the field of physics with precise mathematical language, when you say a bond path is present, there is no way anyone can contradict that statement. Try as they might. They're simply showing their ignorance of the theory. Look at it. It meets all the requirements of bonding. The accumulation of density between the nuclei, which lowers the potential energy, has the effect in the end of increasing the kinetic energy unavoidably. Well, now here's something that really upset a lot of people. It turns out that these polybenzenoids, the bent ones, are more stable than if you straighten this out, you get anthracene, phenanthrene. These are more stable than their straight chain analog. Why? Because look at, there are bonds between hydrogen atoms. Here's a bond path between these two hydrogens, and it forms a ring critical point. Two of them, here's biphenyl. Biphenyl in its equilibrium geometry is twisted. You make it planar, and you go through a transition state. But there, you go through a transition state because to get there, you have to stretch this carbon-carbon bond. That's what the energy increases from. At the same time, the energy is decreased by the formation of these bond paths between the hydrogens. The turmoil that's created. How can you possibly, everybody knows that these forces are, these hydrogens are repelling one another. And you say, what's the force? Well, I don't know what the force is. We'll make up a force. It's an equilibrium geometry. There are no forces. The Ehrenfest force is attractive, and of course the Feynman forces are zero. It's an equilibrium geometry. So what's repulsive? Well, now of course you get them not only here, you'll get them whenever you push hydrocarbon molecules together. Why does solid methane exist? Because you get bonds, paths, linking the hydrogens. In any condensed material, you're going to get bond paths that determine how molecules stick together when you condense them into the solid state. They're predicting the structure of solids in terms of these bond paths, their presence. Well, I don't know. People are still publishing papers to say that there are actually repulsions here. Now, 2 words in Laplacian, I'll quit. Where is the Lewis model in all of this? The topology of the electron density is exceedingly simple, peaking at the nuclei, going through minima and back up to other nuclei. Where are the lone pairs? Where are the bond pairs? Well, you don't find them. But if you go to the topology of the Laplacian of the density, you recover all of this. We covered all of this. Now, the Laplacian of the density, the Laplacian of any scalar, if you read a book on mathematical physics, tells you where that scalar function, the electron density, is locally concentrated and locally depleted. That's amazing. So this Laplacian, now this is all determined ultimately, I might not have time to explain this, to the pair density. The pair density is a condensation in real space of everything that happens between electron pairs in 6-dimensional space, where the Pauli principle is operating. So here is an example of the maxima that you get in the Laplacian of density for the CLF5. Have you had Gillespie's model of Vesper geometry yet? Well, whatever. Here you get a very large non-bonded pair, and then 5 smaller bonded pairs. And the Laplacian recovers the shell structure of a system. Now, not only does it give you the maximum, it also tells you where the minimum are. And all of chemistry is simply sticking maxima into minima. These ideas were first put forth by Fisher in the lock and key analogy, by Paul Ehrlich when he said, look, when you get sick, it's not because you go outside and inhale some vapors in the damp air. You get sick because the bacteria produce chemicals that sit on what he called receptors in your cells. He introduced the whole idea of a receptor and how these receptors could be blocked or activated or deactivated by placing chemicals that you could introduce or might come from the presence of bacteria. He had a lot of trouble getting people to accept that idea, but of course now there's a multi-billion-dollar industry on this, right? So, well, here's chromium CO6, a good example. Here's the chromium Laplacian, and it's got maxima and holes. And here are 6 carbon monoxide molecules. Each carbon monoxide molecule, you see, has a very pronounced non-bonded charge concentration on the carbon, so why it's such a good ligand. And you'll see that each of these non-bonded charge concentrations is directed at a hole in the chromium. So every time you get a lump, it's directed at a hole. This explains acid-base reactions. It explains, look at here, and I really will stop here, okay? Solid chlorine has a layered structure. Everybody said it should just be a simple van der Waals solid. It's not. How do you explain a layered structure? It's a layered structure because look at, here's the electron density, the bond path, their bond path, of course, between the 2 chlorines in a chlorine molecule, but between different chlorine molecules, particularly these 2. Here's the Laplacian. Each chlorine has a torus of charge concentration around it. And each of those torus is pointed at a hole. The hole of this one, the maximum of this one is pointed at the hole in that one. The hole in this one is pointed at the maximum of that one. You can just take one of these diatomics out and calculate the geometry and the properties of that, and it's almost identical to what you find for the dimer in crystalline solid. So suddenly you see it's very easy to understand why solid chlorine has this crystal structure, this layered structure. You're lining up the lumps with the holes. I'll stop. I'll just flash what you're missing. Here. Make it a big molecule from pieces since they're transferable. Make the pieces in small systems and stick them together. Current densities, the first divergence free of induced currents. Carbon dioxide, here's the ring current in benzene, okay? All from the theory of atoms and molecules, which says if you're interested in the current, don't look at orbitals, calculate the current. Is there a ring current in benzene? Well, how do you answer that question? Calculate the current, which was a really big job because the other methods, using orbital methods, gave you lousy results. But using atoms and molecules, you get this beautiful result. You say, yes, there is a ring current. There it is. And I've got one final slide I forgot. And really, this is the last one. I can see no reason for anyone doubting the zero flux boundary condition is a fundamental property of matter, providing the basis for the generalization of physics to its atomic constituents, even at the relativistic limit. Now remember, what's important here is the atom. And the atoms come before the bonds or the bond paths. When two atoms touch, they're separated by an interatomic surface. If you have an interatomic surface, it's inseparable from that. There has to be a bond path linking the two atoms, okay? But the presence of the bond path is just a easy, quick way of summarizing which atoms are sharing interatomic surfaces. If you start drawing all the interatomic surfaces, it looks very complicated. But isn't it remarkable that this shorthand notation, drawing bond paths, to show which atoms share a surface, is precisely the notation that evolved from experimental chemistry. Now, I can't think of a stronger case in favor of the zero flux definition of an atom other than that. You look at any structure you like, and that structure is going to be, here's some DNA base pairs. You see that in the molecular graphs? All there. You'll find that always, I don't care how complicated a system you take, you'll find the bond paths give you the structure, and now you can study that structure quantitatively, see how it changes, and I'll stop there because I promised. Thank you. Okay. Oh. May I keep it? May I keep it? This.
Should we vote?
Yeah, right. Okay. Yes, you're going to translate for me. I forgot my hearing aid, so he'll tell.
I'll speak loud. Probably one thing that Ralph Hoffman is concerned about is how do you explain chemical reactions that are not explicable in terms of electron density that have been explained by Hoffman
Oh, wait.
in terms of, in terms of orbital symmetry.
Okay, look at
What
it.
is the orbital symmetry?
Yeah, all right, look at it. The first symmetry rule of quantum mechanics was given by me in 1961, okay? And orbital symmetry, when applied properly, is using second-order perturbation theory. And what you do, if you plot an orbital correlation diagram, which I did for a loud reaction, you'll find that when you get to the transition state, and it's a loud reaction, gee, you generate a low-line excited state. And this low-line excited state of just the right symmetry, that when it mixes in with the vibrations, it'll make that vibration the favored vibration and give you a reaction. If you, just a minute now, just a minute. If you take a reaction that's not allowed, then you find you don't generate this low-line excited state, and the energy just keeps going up. Now, there is nothing. I mean, am I saying you should forget orbital symmetry rules? No, use orbital symmetry rules. Of course you want to use them. But in the end, you could relate anything you find, of course, to changes in density, to the making and breaking of bond
But
paths.
density doesn't have phase.
Yeah, look at. The quantum mechanics of an open system is not the density. The density defines the boundary condition. But the physics is described by quantum mechanics. There is nothing that is left out. And don't feel that lots of people say, oh, what, the density doesn't have this, the density doesn't have that. It's not the density. That provides the boundary condition, which it must in real three-dimensional space, right? How else would you define a boundary condition? But the quantum mechanics is complete. And you can calculate all properties.
So
Energy
this is not
changes.
just plus just electron.
You can combine.
Then the
you
nucleus
could-
and the electrons attracting each other in a,
Yeah.
in a non-quantum mechanical way. So what,
What?
you're just
What's none?
you,
You've lost me. What's non-quantum mechanical?
just plus positive attracting negative. Just electrostatic.
Yeah, it is.
That's not quantum mechanical.
Yes, it is. Look at it. That's what I'm saying. It is quantum mechanics. Look at it. Look at it. Look at it. Here, look at it. Look at it. Let me go back. Let me go back. You've missed the point. Missed the point. Let me go back one slide. Here. What is quantum mechanics? You start with the forces define the Hamiltonian. Okay? If they're conservative, you can define the Hamiltonian. Even if they're non-conservative, you can still deal with it. You get Schrodinger's equation. You solve Schrodinger's equation. Then you go through, if you want to transform, you use Dirac's transformation theory. Finally, you get the equations of motion. Once you get to here, you use this wave function, determine this property. You get all properties and all equations of motion, and you can understand all the properties of a system. What Schwinger did was show that everything on this slide, given Dirac's transformation theory, can be derived from a single principle. What we did was show that that same principle, including the derivation of this, applies to just an atom and a molecule. Now, there is nothing you can predict using Hoffman symmetry rules that you cannot predict in quantum mechanics. I'll stand by that.
Okay, are there other questions?
Okay.
Professor Matiescu.
A take-home lesson for these young kids. Their children should start taking quantum mechanics in high school. Because indeed, the whole science that we are here to learn is based on quantum mechanics. And the huge mistake of the education system today is not teaching you in time quantum mechanics.
Are there other?
And besides that,
I really do. That's very good.
that's what he said, and you are so darn right.
Thank you. Everybody hear that? Thank you very much. No, but I feel very strongly about this. It really is time physics took back chemistry, and we stopped statements that, oh, chemistry lies beyond physics, and you can't explain this, and you can't explain that. What can't you explain? What measurable property is not predicted by quantum mechanics? All right? Yes.
I have a question.
Okay, let me come closer, because I forgot my hearing aid.
You showed a picture of a carbonyl, metal carbonyl system vibrating.
Yes.
And you showed the
Change in structure.
well, also the ring critical points appearing and then disappearing.
Yes.
Let's go to a very simple system, like a diatomic.
Yep.
And I have equilibrium bond length.
Are you going to push them together?
No, I'm going to pull them apart, and at some point, I'm going to lose my
No, it'll be there, infinite separation, all the way. The minute you start putting them together, you start accumulating electron density between them. I mean, they'll be minuscule. You won't be able to detect it until they become, say, 10, 12 atomic units apart. But the bond path persists. It persists.
If I'm like many 20
Yeah,
angstroms.
they say hydrogen atoms in outer space that might be 1,000,000 light years apart. There's a bond path connecting them. This disturbs some people. It's not a useful idea.
Oh,
There's
it's a
nothing you
limiting
could do.
idea.
There's no physics associated with that. I don't think. Who knows? I mean,
Okay, thank you.
okay. Yeah, all right. Did I explain it okay? See, I thought you were going to say if you push them together, does that line vanish? No, but then it's no longer a bond path. It's what we call an atomic interaction line. If you take any diatomic molecule past its equilibrium and push it together, you don't suddenly lose that line. But then it no longer fits the definition of a bond path. There's still a line of maximum. Now it's telling you which atoms are repelling the most, right? Which is just as useful as to which atoms are attracting the most. Yeah. Thank you.
Okay, any other questions? I'd like to make a comment that I thought that in some of the high school books, or at least freshman books, they talk about an electron glue between, which is kind of the Hellman-Feynman theorem in a very simplistic way.
I haven't seen those. I'd be
Yeah,
happy to.
I remember seeing that and mentioning it sometimes in classes. Have you heard, you students, of electron glue holding the atoms together?
Okay, so we have freshmen here. Do any of the books you use in freshman chemistry here have anything about the Feynman forces on nuclei?
But
About the electron density?
about the electron glue, which is a simplified version of the Hellman-Feynman theorem concept. In there, maybe, he says, yeah. But the formulas aren't there, of course.
But they're very simple.
I have a question. You had the chromium, and you had those holes in the Laplacian.
Oh, yes.
That's, is that for the free atom?
No, that's for
Okay.
the chromium atom in that
Right.
compound. Sorry.
So if you, as far as the predictive capabilities are concerned, you have to have the densities at the beginning from quantum mechanical calculations.
Okay, but hang on, let me make this clear. People used to say, oh, but Richard, you need the quantum mechanics to answer. How do you predict anything in quantum mechanics without using quantum mechanics, first of all, to get the wave function? Once you learn about these things, now I know about the Laplacian for these metals, now I'll make predictions without doing a calculation. Like anything else, once you learn the properties of some property of such as the Laplacian, then you, oh, I know what's going on here, and I know why you have this geometry. This lump will be interacting with that hole. And sure enough, you go and do the calculation, and you find that. But yes, you have to, I mean, in the normal case, you have to use quantum mechanics to get the wave function, to get the density, to get all the properties.
Right.
Okay? Right.
Okay,
That's not a detraction, that's just the way you do physics, right? Right.
I guess there are no further questions, and
Oh, come on, that's still early, it's only 5:30, sorry, whatever.
and if not, let's thank Professor Bader again.
Thank you. And again, I thank you for giving me a chance to vent a little bit, okay? Thank you. Right. Okay. Well, was it all right?
Yes.